lecture in this topic is basic optics for light microscopy. And it took me many years. I'm a biologist myself, and it took me many years to learn all this, unfortunately. And I try to crystallize it in such a way that we only talk about the things that are important for us microscopists who image biology. So light changes its behaviors when it reaches boundaries. But when light travels in a heterogeneous medium, so we have established that our samples are heterogeneous, it may encounter a new medium or an obstacle. So, for example, the light will go through the objective and then suddenly it reaches the cover slip. So what happens there? So when this happens, four things can happen: reflection, refraction, diffraction, and interference. So I'm going to talk about each of them. So reflection, this, I think we all know what it is. It's at the boundary between two different media. So we have a medium here and we have a medium here. But the light does not come into the second medium. It just bounces off at the boundary, right? This is reflection. And the light bounces off without continuing in a second medium. So here we have the representation as a ray optics, and here we have the wavefront. And you can see that the wavefront here has the same shape and also the same distance between the crests. So it has the same speed and the same shape. It's here. And this is exactly what happens when we see this little cat in the mirror. We have the same image. The image here is not distorted. Everything just bounces off, and that's it. And the light does not go through the other side. So there's a change of direction, but the shape and the speed of the wavefront stay unchanged if the boundary is flat. So what is the relevance for us? Well, in the microscope, there are lots of mirrors, and mirrors are used in the microscope to direct the light back and forth throughout the whole microscope. So mirrors are very important for us microscopists. And one consequence of this light being reflected is that if we have a very strong light, you will see that it's the same thing as if you want to, you pass by in the evening and you see a dress in the window of a shop, and oh, I love this dress, I want to take a picture of it. And you take out your phone and it's dark, so the phone is going to turn on the flash. We have a very strong light in front of a reflecting surface, which is the window. And this is what happens. You're not going to see anything in your image. And this exactly the same thing happens in microscopy. And to avoid this, when we shine some very strong excitation light, we have dichroic mirrors. And so we will talk about the dichroic mirrors. You have already seen the video yesterday, hopefully. And so you know already what dichroic mirrors is. This is what they do. They eliminate this very strong reflected light. So reflection is a very important thing in light microscopy. We use it, but we also have a problem with it, so we can get rid of it. Now let's talk about refraction. Now what happens now is that we still have two media. So we have a medium here and a medium here. And the light reaches the boundary between the two media. When refraction is what happens when the light passes into the second medium. So it passes the boundary this time. It continues into the new medium. And you can see this in here. This is something you may have seen done to your parents as a kid. Look, Mom, my pencil is broken. Here we have air. So sorry, I'm a bit ahead of myself. So there is a change of direction. You can see in here, there's a change of direction when the light enters the new medium at an angle. So if it comes perpendicular, it will keep going straight. But if it comes at an angle, it will continue with a change of direction. And also the shape and of the wavefront is unchanged. If you see here, it's flat, and here it's also flat. If the boundaries is flat, then the shape is not changed, but the speed changes. So both the direction and the speed change. And this is what makes this pencil look bigger in here. So the light is distorted, and the image is then distorted, the image that we form on our eye. So this medium and this one here, the water, and here the air, and also the glass, all these media have a refractive index. And the refractive index of the medium is always called N. I have no idea why, but there must be a reason for this. So when you see a little N like this, it's the refractive index of the medium. And this is a measure of how much the medium changes the speed and the direction of light compared to air or vacuum. So the refractive index of air is 1. This is sort of the reference. And glass is 1.52 and water is 1.33. So throughout the course, because in microscopy we use glass, we use oil, we use water, we're going to use all these numbers quite a lot. So you don't need to sort of strain yourself to remembering now. You will remember by the end of the course, I'm sure, because you will use them a lot. It's not so many also that you need to remember. So this is the refractive index of the medium. So, and there is a law that regulates how much the light is bent and when it goes from one refractive index to another one. So it's proportional, basically. Same thing. You don't need to remember this equation. Just know that it's proportional to the medium. The thing is that different wavelengths, so different wavelengths means different colors, right? Different wavelengths refract light differently. And that leads to dispersion, which is the rainbow that we were talking about yesterday. So in here we have a piece of glass, and there is an angle here with the direction of the light. So the light comes in this way, and this is white light. So you can see that we will have different wavelengths in that light. That's why it's white. And we have here a boundary between two media. So here we have the air. So the refractive index is 1. And here we have glass. So refractive index 1.52. And because of that, we have refraction here. But different wavelengths in this white light will refract differently. So we get a rainbow. And this is exactly what happens in the air when it rains, because the light goes through the fine particles of air, and there are so many small particles when there is a cloud or when it rains, that the light actually diffracts on each particle, and at the end there is dispersion. So we get a rainbow. And then going out again from glass to air, then we get again another dispersion. Okay, so this is very useful in microscopy. We can use it, so why is it relevant for us? We can use it in spectral detectors. So many spectral detectors use dispersion to split white light into its color components. So there are different ways to disperse lights. Some microscopes use a grid and others use a prism, but it's the same principle. Another thing that is for which refraction is important is because our samples are unfortunately made of heterogeneous matter. We have a lot of different material in the sample, the proteins and the lipids and everything, and each of them has a different refractive index. And therefore, in a sample, we have a lot of different refractive indices, and the light has to go through all these refractive indices, and every time we have refraction. So light refracts at each refractive index boundary. So when we have we pass the lipid membrane, and then when we go in through the nucleus, etc., we pass boundaries, refractive index boundaries every time. Sorry, is that working here? Yeah. So when we prepare our sample, we will talk about this in the sample preparation. The best way to prepare a sample is to place, if you cut a tissue section, is to put it directly on the cover slip and not on the slide. So when you cut your sample at the cryotome or something, we always tend to collect the sample with the slide. But what you would want is to put it on the cover slip and then put the slide on top. We will talk about all this in the sample preparation lecture with Gabi. It also influences the choice of objective that we have. So what we would like is to match the refraction indices of the objective immersion medium and the sample to avoid that the image is distorted. So the light is, both the excitation light and the emission light are going to go through the objective. So there's lots of glass. And then we're going to go through the medium that you put on top of the objective, which is the immersion medium. And then you're going to go through the cover slip, and then you're going to go maybe through your mounting medium, or you're going to reach directly your sample if the sample is on the cover slip, etc. And so normally we want to try and have as few refraction index interfaces as possible. So it has an influence on our sample preparation, on the choice of objective, and also inside the microscope, light travels from air to glass through all the lenses. It goes through air and glass to air all the time, and every time there is refraction. And that means that we can actually use lenses and the fact that there is refraction at each interface to manipulate light. And this is what we're going to talk about now, how we can use lenses to manipulate light. So refraction can be bad, but it can also be good for us because we can manipulate light. So the next behavior of light at boundaries is diffraction. So this is when light reaches, so it travels through one medium, but it reaches a solid obstacle. So there's only one medium here. Here is one medium, and it's the same medium here. But here we have an obstacle, and this obstacle is not possible to go through. So the light will travel next to the obstacle, but just next to the edge, it will actually continue past it, but it will be transformed here, and the wavefront is bent around the edge. Okay, so even though light continues here, as we get closer and closer to the edge, there is diffraction and the wavefront is bent. And this is something that you can see in nature very easily. So if you wonder why most beaches are sort of rounded, it's because usually you have a stone here and you have a stone here and you have diffraction there, and that bends all the waves that come. So here we have a flat wavefront. I don't know if you can see here, but the waves are aligned sort of in a flat way. So we have a flat wavefront, and the waves continue on the surface of the water in here. And so the wavefronts are still flat here, right? But if we look closer to the pier, then we can see that the wavefronts are curved. And so there is a reflection a diffraction, of the waves closer to the pier, and then we get this curved wavefront. So the same thing exactly happens in microscopy, except that it's not 2D. So this is a surface, the waves on the surface of the sea is a surface, so it's 2D. But for us, in microscopy, it happens in 3 dimensions, so in X, Y, and Z. And in microscopy, every molecule in the sample is an obstacle and diffracts light. And the inner edge of the objective, so the light is coming from the sample and is going to get into the objective, and the edges of the objective inside are also a hard boundary, and there we have light diffraction. Okay, so we have a lot of diffraction going on everywhere in the sample and in the microscope. And actually, I'm going to tell you about this now. Image formation comes from diffraction and the interference of light in 3D. So diffraction is very important for us, otherwise we would not be able to image. So now we're going to talk about interference. What is that? Well, we'll talk about diffraction and how the wavefront is bent after an obstacle. So again, here we have the surface of the sea. We have a flat wavefront here, and here we have an obstacle that the waves cannot go through, so they bend on the edges. Here we have a curved wavefront. Here we have also a curved wavefront. All this is due to diffraction. But what happens here, where the waves are meeting, the curved waves are meeting, and what happens also here, because it's the same thing, we have a curved wavefront here and a curved wavefront here. This is interference. So what happens is that at this place, the waves bump into each other, and they are adding up or subtracting each other. So it's called wave interference, and it can be constructive, where the final wave is bigger than the other two. It's a sum of the two, or it can be destructive in a way that you can have no wave at all, because they're sort of not in phase and they're distracting each other. I'm sure you remember this from your school time. So when the waves travel into one medium coming from different directions and they bump into each other, the amplitudes add or subtract. And so this is called constructive or destructive interference. And it makes an interference pattern at these places. So we're going to have a different pattern at the places where we have interference. And why do we care as macroscopists? The wave is regular. And the waves at the surface of the sea are not very regular, but light is a very, very regular wave. Then the interference pattern is highly predictable. And if it's predictable, we can use math to predict it and to manipulate it and to see what is going to happen. And this is why this is what happens basically with light. So it's highly predictable. And the interference patterns carries information about the wave, but it also carries information about the obstacle, which is, for us, our sample. So if we look at the interference pattern, we can learn things about the obstacle. When we record an image, what we record is actually the 3D interference pattern. So this is the way light, an image of our sample is formed. It is a 3D interference pattern. That's exactly what we are recording. And that means that anything that affects the interference pattern is also going to affect the image. So our job as a macroscopist is to try to keep the interference pattern as clean as possible. And we will talk about all this, how to do that. So one way I've also said that we can use all these phenomena, diffraction, refraction, reflection, and interference, is to manipulate light in the microscope. And in microscopy, we manipulate light using several objects and lenses and irises. So if I look at lenses, we see that we've had diffraction because the light comes in at a certain angle and the surface is flat on one, maybe flat, maybe not flat. And then we change the direction of light, we change its speed, and we change the wavefront. So here is refraction that I was showing you, and the wavefront is not changed only if the boundary is flat, but in lenses, we sometimes there are lots of different shapes of lenses. Sometimes they have a flat edge, but mostly they don't. And anyway, even if they have one flat edge, they only have one, and not the other one is not flat. So in lenses, we always have at least one side that is not flat. And in objectives, you can see that objectives are very complex. There's a lot of lenses in them. So the light will go through all these lenses. And what happens is that we have refraction and refraction again, and that allows us to focus the light. So we can have light that is completely defocused. We can put it through one lens and focus it as we want. And then we can do the opposite afterwards and defocus the light. And this is the way we use refraction to modify the light and to manipulate it. So in here we have air, the refractive index is 1. Here we have glass, the refractive index is 1.52, and it goes back to air and equals 1. And therefore we have refraction and we focus the light. In here, the wavefront is going to be flat. Light is going to propagate this way. But in here, we have a curved wavefront, and therefore we have a focal point. So the way we use lenses is that it changes light direction, speed, and wavefront. We can manipulate light this way. And you probably remember from your school time that sometimes this is shown as a little candle, that we can say, oh, this is our sample, and then we use a lens. And with ray optics, we can show that we're going to get an inverted image. And this is the intermediate image plane. This one would be the sample plane. Here, intermediate image plane. And then we're going to put a second lens and get a final image, which we can record. So what we're doing here is that this lens is used to transform the light that comes from the sample. This one is used to make an image of the image. So we have here an image, and here we have the image that is made from this first image. So we have this intermediate image plane. It's exactly the same that happens in our samples. So in our sample, each fluorophore is actually a light source. right? It's like we have lots of little lamps inside our sample. So the fluorophore is going to act like a light source and it's going to shine a lot of light, and this light goes in all directions. And we have a curved wavefront. The light is escaping from the fluorophore in each direction. And then we put a lens in front of it, and we transform this light from a curved wavefront to a flat wavefront. So this would be the objective front lens, and this would be the edges of the objective, for example. Then we have a flat wavefront. And then we put another lens, and now we get a curved wavefront, and we get an intermediate image. We get this image in here, and then we're going to do the same thing and transform again the light until we get final image plane. And what we do here is that we record. So this is where we put our sensor. It can be detectors, it can be a camera chip, but this is where we record. So what we're recording is the final image. This is the way it works for every single fluorophore in our sample. So in microscopes, there is refraction through each of the lenses, and there is a space where some places in the microscope where we actually have an image, and everything else in the microscope, everywhere else in the microscope, there's no image. So we have some sample planes where we have an image, and then there is the rest without images, where the light travels, but there's no image formed. So now the second way we manipulate light is with irises. And irises look like this. You can close them and open them. So they can be called two different things, field stops or apertures, depending on where they are in the microscope. So here we have again our microscope. So it's a microscope that's laying down. Here we have the sample, and we have the objective here. We're forming an intermediate plane, and then we're transforming the light again until we get the final image, which is what we record. And now we're going to put irises there in this light path. And if we put the iris in an image plane, the iris is called a field stop. And what we do is that what happens is that it is then visible in the image because the iris is together with the image. Then when we close the iris, we're going to see it. So when it closes, it blocks the light like a curtain. So in here, we see the edges of the iris. And if we close it even more, the outside of the image becomes black, like a curtain. So a field stop is in the image plane, and it only affects the edges of the image. The center of the image looks exactly the same in here and there. However, we put an iris outside of the image plane. There is also light here, but the interference pattern happens only at the image planes. So if we put irises outside of the image plane, they're called apertures. And they are not visible in the image because we have no image in here. So they are not visible in the image. And what happens is that they prevent the light from forming the interference pattern. So we're affecting the whole image when we close the aperture. It prevents some of the light from participating to the interference pattern at the next image plane. So it affects the whole image, not just the edge. So you see this image becomes darker, but in this image we cannot see it, but also you will get a little bit more contrast in the image and maybe even a better resolution. So it affects the image a lot to close an aperture. Clearly it affects the image a lot to close a field stop as well, but here is quite easy to see. Whereas this is a little bit counterintuitive. If you close an aperture, you will affect the whole image, not just the edges. So why do we care about irises and where they are? There's a lot of relevance. Actually, in the microscope, we have field stop at different places, and they are used, for example, if I only want to image this part of the sample, and I do not want this part to be illuminated because I don't want to bleach it, for example, then I will use a field stop to only illuminate this part of the sample. This is one way we can use a field stop in the microscope, is to prevent illuminating places that we don't want to illuminate. Another way to use field stop is when we do color illumination alignment. So we will talk about that later, and you will have to run the color illumination alignment on your microscope. Color illumination is a way to align the condenser when you want to do transmitted light imaging. So we will have to do this later, and for this you will use a field stop, and you will see that when you close it, it becomes like a curtain like this. So this is something you will also experience on your own microscope. Apertures on the other side, they are not visible in the whole image. They affect the whole image. They do not affect only the edges. So they are not visible. It's difficult to see it in the image. You don't see it on the edges. But they are used to adjust the contrast in transmitted light. And this is also something that you will do when you run the color illumination adjustment on your microscope. But also, and very importantly, the inner edge of the objective acts like an aperture. So the objective is, and put it like this, the objective is a physical device. There is an edge to it. When our sample starts fluorescing everywhere, only some part of the light will enter the objective, and the edge of the objectives are an aperture. So the objectives have something called a numerical aperture. Some of you might have heard of the numerical aperture of the objective, and I asked you to collect some information about your objectives, so we will also complete this information later. So each objective has a numerical aperture, which is a number that is written on the objective, and this means that it's a very important number. When we have a small numerical aperture objective, less light is involved in building the interference pattern and image plane. So our images are going to be dimmer, and then we're also going to have a lower optical resolution. So the numerical aperture of the objective is something we're going to talk about throughout the course. And now you know what it does. It actually modifies the whole image because it's an aperture, okay? And the optical resolution, as a definition of what is the optical resolution, it is the resolution that is delivered by the objective at a given wavelength. So we will use the optical resolution a lot throughout this course. But now you know why if you close the field stop on the microscope, you're going to see the curtain effect, and the center of the image is not going to be affected. Whereas if you close an aperture, or if you choose an objective with a smaller aperture, then you have an effect on the whole image because it affects the interference pattern. So the final resolution in the image can be limited by different things, and this is something that we will build throughout the course. It can be limited by the optical resolution, which is limited by the objective and the wavelength. It can be limited by the digital resolution, which is the sampling and the pixel size. So this is the way we record the image. And it can also be limited by the contrast and the sample quality. So throughout this course, we're going to try to tackle all this and try to see how we can improve our image in all ways. So here are the conclusions for this little part of the lecture. In a microscope, light encounters different media and obstacles, and leads to different behavior of light, reflection, refraction, diffraction, and interference. We can manipulate light using lenses, so we change the direction, the speed, and the shape of the wavefront. But we can also use them to focus the light at image planes, and this is very useful, clearly, in a microscope. We can also manipulate light with irises, and field stops act like a curtain, and apertures affect the quality of the whole image. These two are the same thing, they're irises, but they're placed at different places in the microscope. So I'm looking again at my timeline, and